All right, welcome to our 7th video of Unit 4. This one's talking about Hess's law. So enthalpy is what we call a state function. That means it depends only on the current state of the system. A long while ago, my brother and I decided to go hiking in Yosemite. This down here is what we call Clouds Rest, or not Clouds Rest, Half Dome. Pretty common peak in Yosemite. We decided to climb Clouds Rest, which is actually quite a bit taller than Half Dome. Now, here's the thing. It has a crazy high elevation that I don't remember. We decided, however, to take, well, to be honest, kind of the hard path. It didn't really go too well. We didn't quite finish our trek. But here's the thing. Even if we would have taken the same path or a different path, we would have ended up at the same elevation. So this person, whether he came from this way, or maybe, the other side of the mountain, he's at the same elevation. That is what we call a state function. So elevation, for example, it's something that does not depend on the path you took. It depends on where you are. However, our feet and the distance we traveled, well, that wasn't quite a state function because we took the hard path, which wound about, and that was really hard to get to. So the different paths you take are not state functions because you travel more distance going this way than, maybe straight across or maybe a different path. Enthalpy, though, is what we call a state function. So the enthalpy change for a reaction depends only on the initial and final conditions, not on how it was taken. Meaning, if I gain, if I end up producing 20 joules in a reaction, that reaction maybe have 5 steps. And maybe in some steps it gains energy, some it requires, but it equals out to producing 20 joules of energy. I don't really care how I get there, I just know it will eventually produce 20. So whether it occurs in one step or many, my enthalpy change remains the same overall when I at least combine all those together. That is Hess's law. So more specifically, Hess's law states that the enthalpy change associated with a reaction that is carried out in multiple steps is equal to the sum of all the enthalpy changes for the individual step. Typically at Thanksgiving time, you may have a very, very big, turkey dinner. That's actually it's a turkey. But if you look at this turkey dinner, there was time spent for cooking the turkey and making that sauce thing and making all this other stuff, okay? What Hess's law says is that even though the turkey may take multiple hours and the sauce takes all this stuff, the combined total for making this dinner is just equal to the sum of all the times it takes to make all the different parts of the dinner. Which, my hope is, that makes sense. If step 1 is cook the turkey, step 2 is do whatever, it's just, all you have to do is add up the total times. So in Hess's law, if you can show that multiple reactions add up to one reaction, then the enthalpy of that added reaction, like the final, is just the sum of all the other ones that make it up. So let me show you. Before that, though, when performing Hess's law, there's 2 things you got to remember. First off, delta H for a reaction is equal to negative of that of the reverse. So that means if I produce 10 joules going in my forward reaction, I'm going to require 10 to go backwards. Secondly, if all the coefficients of reaction are multiplied by a number, then the delta H for that new reaction is equal to the original delta H by the same number. Meaning, let's pretend I've got A, producing B. My delta H is 10 kilojoules. That says that 2A to 2B, my delta H is 20. That also would say that B to A, my delta H is negative 10. So there you go, just kind of a summary. All right, so you have more words in your example, but they really wouldn't fit. So this says, basically find the rate, the enthalpy of this reaction given these. Well, if you look at these reactions, if we were to add these 2 together, we are not going to get this top one. Because if you look at the top, diamond is a reactant, and down here we got diamond as a reactant. However, graphite's a product. Graphite's not a product here. And also, what the heck is this O2 and CO2 doing? So the biggest thing you do in Hess's law is you pick the reactants, you basically make let me try and figure out how to word this. You go chemical by chemical in the reaction you're trying to solve for. You find what reactions have that chemical, and you make those reactions look like your final. Meaning, we start with diamond. We say diamond has to be reactant. We find whichever one deals with diamond. There you go. We say, all right, diamond needs to be a reactant. Well, it is, so this reaction's okay. I'm going to put a little check mark next to it. Then we find graphite. Graphite has to be a product. Graphite is not a product. That means we need to switch this equation. So what we're going to do is I'm going to write CO2 over here. Make sure you keep the states. Okay. And I'm going to cross that out. I basically write the products of this reaction as my reactants. I'm basically flipping my reaction. And then I write my reactants. S, graphite, plus O2 as a gas. And then my delta H goes negative. Okay, that is supposed to be the negative of that. And there you go. So now we check again. Diamond's a reactant, graphite's a product, so we're okay. Now what we do is we basically add the reactions together. Well, yeah, now I'll tell you the easier one. I don't really want to. Now what you got to realize is that at some point, O2 is a reactant and O2 is a product. If O2 comes in as a reactant and leaves as a product, that means it didn't do anything with our reaction. We don't need to really care about it. So, in Hess's law, we cancel it out. Okay? Same with CO2. I'm actually going to squiggle this out more just because it's kind of confusing me. CO2. It's a product on the first one, reactant on the second one. So we cancel those out. And then, once you're done canceling everything out, you write whatever you've got left. So carbon as a diamond produces carbon as graphite. Now that's actually the equation that we got, that we were looking for, except we got to remember that we got this by adding those two equations. So that means our delta H at the end will equal negative 395.4 plus 393.5, which equals negative 1.9 kilojoules. So that says that as I convert diamond to graphite, I'm going to release about 1.9 kilojoules of energy. And that's Hess's law. It looks really confusing at first, so let me kind of remind you. You take chemical by chemical, you make sure that your reactants actually look like what it says in your final reactant. You cancel out things that appear both as a reactant and a product, add everything together, add your enthalpies, and you're done. That's it. We'll show you another example. All right, we got a longer, scary looking one. Okay, these three are helping us to get this. So we start chemical by chemical. Actually, I'm going to give you a chance to go ahead and pause this. I'll give you about 5 minutes. Try this on your own, because let's see how well you get it first off. So go ahead and pause, try it. All right, hopefully you tried it. Let's see how it goes. We need calcium as a reactant. We have calcium as a reactant. We need carbon as a reactant. We have carbon as a product. All right, that's an issue. So, however, notice we have 2 carbon up here. So if I have 2 carbon as a reactant and 1 carbon as a product, I can kind of cancel off 1 carbon from both sides. Thus, instead of having kind of, basically we're saying 2x and x, I can just say x. Or in this case, since I know x kind of scares a lot of people, if I have 2 carbon, arrow and arrow carbon, I can just say I've got 1 carbon. And 1 carbon is exactly what I need. All right, So that means I'm good on carbon. I need 3 halves O2. Well, we have an issue with that. See, I have 5 halves O2, and I have an O2 up here. Now 5 halves, I can get from 5 halves to 3 halves. I just ultimately need to subtract 2 halves, which is just 1 O2. But we also have another issue. Like, we'll come back to that because we have O2 somewhere. Let's look at COCO3. That needs to be a product. I have it as a reactant. So we need to actually flip that. So that means we get Ca C2 as a solid plus 5 halves O2 as a gas produce Ca CO3 as a solid plus CO2 as a gas, and our delta H is negative 1538. All right, let me cross that off a few times. Okay, so we have calcium, we have carbon with those subtracting, we have 3 halves O2. Oh, by the way, when you're doing these problems, it really helps to line up the arrows. I'm sorry I didn't. I honestly just kind of didn't think about it. But that really, really, really helps you. That way you can really see which things are reactants and products, which thing can kind of cancel out. It just really makes your life a lot easier. Anyways, though, we have calcium carbide. Really isn't involved in this equation, but you'll notice up here it'll cancel out. 5 halves O2 will hopefully deal with calcium carbide, carbonate's a product, and we got this weird carbon dioxide thing going on. So I think we're okay. Now I'm actually going to rewrite these equations. Just I'm going to erase the enthalpies, but I'm going to kind of show you canceling out. It helps when they're lined up. So hang on. Okay, so I didn't write the enthalpies, but this is basically our equations kind of rewritten and lined up with an arrow. So now we can kind of start canceling things out. We have 1 carbon here. That'll take off that 2, so we just have 1 carbon. We have a carbon dioxide here, and we can cancel that off here. And we have 1 O2 over here, which I'm going to kind of rewrite as 2 halves. 2 halves, 5 halves. 5 minus 2 halves gets us 3 halves, which is exactly what we want. Okay? And I don't think I can cancel each other out. That means that when I add those together, calcium carbide, calcium carbide. That means I will get calcium plus 3 halves O2 produce, so calcium, 3 halves O2, produce calcium carbonate. So that shows that our equation does actually balance out. I'm going to let you write that down real quick, and then we'll deal with the enthalpy. So give me just a second. Actually, I can do it up here. So that means we added this one, and we flipped this one. So that'll be negative 62.8 plus 393.5 plus a negative 1538. Add those together and you get negative 1207.3. Now, Hess's law tends to scare people, and you can see why. All you have to do, though, is find your final equation and basically just match up as many compounds as you can. When you hit something like carbon or oxygen that you're just not sure of, try and work out everything else. Eventually, you'll find that basically the reactions are just going to kind of work out. It looks scary, but honestly, they're not that bad. You can do this. But here's some practice. Calculate the enthalpy change for this top reaction. These do look a lot scarier. You might have to, think, but you can do this. Thanks for watching.